Practical uses of differential calculus. You want some notes? No doubt. So what we got is we're going to have a brief look at. So Ryan, do you have any spares? Rate of change. How fast one variable changes with another. The point is the most common engineering application of that. Velocity, or rate of change of position with time. Meters per second, if you like. Yeah? And then acceleration is the rate of change of velocity with time. Meters per second squared. Okay? So problems around that. Finding the turning points for a function and what their nature is. So minimum, maximum, and another one that we didn't see earlier, but a point of inflection in a function. And where you might want to do that, if you were looking at something, a projectile or something, and you wanted to know its maximum height, you'd look for, and you knew a function of its flight, you'd find the point where the slope was 0, you'll find its maximum height because it's going to travel in an arc like that. So if you find the point where the function is 0, so if you could fit a function, then you would be able to find the height at that point, and therefore you're using differential calculus to do so. Yeah. And then practical problems involving minimum and maximum values. So we're going to have see how far we get with this, and then I'll leave you to peruse the rest of it yourselves. Okay. So more about you knowing why you might use these techniques than anything. If a quantity y depends on and varies with another quantity x, then the rate of change of y with x, or with respect to x, is dy by dx. So other examples, the rate of change of pressure with respect to height in a tank, for instance, be dp by dh. The rate of change with respect to time is usually just called the rate of change. With respect to time is assumed when we're looking at rates of change problems. Okay. So for example, rate of change of current I is di by dt, rate of change of temperature theta is d theta by dt, and so on. So the length L meters of a certain metal rod at temperature theta degrees C is given by L is equal to 1 plus that little number theta plus another little number theta squared. Determine the rate of change of length in millimeters per degree C when the temperature is 100 degrees C and where the temperature is 400 degrees C. What do we need to do in that problem? Is determine the rate of change in length. Got a function where the length of this rod is equal to 1 plus 0.405 theta plus 0.12345 theta squared. So that gives the length of that rod at a particular temperature. The question's asking you find what the rate of change of temperature is. Rate of change of length, sorry, at two given temperatures. So what do we need to find so that we can find the rate of change of length? We need the rate of change is the differential, d theta by dt. So we need to differentiate that function. And then we'll find the rate of change. So, differential 1 is nothing. Yeah, differential of all that is 0.405. Go on. No, theta goes, doesn't it? Because that's to the power 1, yeah? That disappears. We've got to multiply that bit by 2. So that's 0.12345 6 noughts 8 theta. Yeah. Simple as that. If you want to find the rate of change and you're given the function for length, rate of change of length, differentiate the function for length and you get the rate of change of length. Yeah. So now we can say at 100 degrees C, d theta by dt, the rate of change, is 0.405 plus 0.608 times 100. And at 400 degrees C, d theta by dt equal to there's another important piece of information in the question. Two important bits of information. What's the answer to this first one? Have you noticed it? The question says the length in, the information says the length in meters. That's why there's this really tiny numbers in the function, because the unit there is meters. Okay? The question is asking the change of length in millimeters per degree C. When you calculate these, you're going to get your rate of change in meters per degree C. How can we get it into millimeters per degree C? Multiply it by 1,000. Yeah. So we could, the alternative would have been to multiply these numbers by 1,000, turn it into length in millimeters. So the answer here is, anyone done it? Sorry? 0. Got to be 1, 2, 3, 4 noughts 5, hasn't it? Or is it not? What? I don't like this example. I'm going to change it. Let's write it like that then. I like that. 1.3 times 10 to the minus 4 meters per second. Yeah. And in millimeters, that is, we multiply that by 1,000, that would be 1.3 times 10 to the minus 1, or 0.13 millimeters. Yep. And this one comes out at 3.7, I think, times 10 to the minus 4 meters per second, which is 0.37. That's expanding at some heck of a rate. Every 3 seconds, it's going to be a millimeter longer. At 400 degrees C. Yep. All right. So, rates of change. Everybody happy with that? And there's a second example in notes that you could have a look at if you want to, about the displacement F's in centimetres at the end of a stiff spring at time t, and so on and so forth. Okay, that one is quite a tricky little one, because looking at the function, what rule have you got to use? We've got S is equal to I e to the minus kt sine 2 pi f t. So what really got to use to differentiate that function to find, I'm proposing we're going to go through this one now. Hey, I'm leaving it for you to have a look at, but what rule you got to use there? Yeah, the product rule. We've got a function there multiplied by another function there. So you've got to use the product rule. Okay? So something for you to have a go at. See if you can get the right answer. And what I will do is I'll tell you what the final answer is for that question. It is 22.55 centimetres per second. That's the velocity at the end of the spring after 1 second. So they're giving you values of A, K and F, and asked you to find what the differential is equal to after 1 second. And that's the answer. All right. Velocity and acceleration. When a car moves, or a vehicle moves a distance x meters in time t seconds along a straight road, if the velocity v is constant, then v equals x over t meters per second, i.e. the gradient of the distance time graph is constant. We get a straight line. where the distance moved in meters as the y-axis and time t in seconds as the x-axis. So our slope of this graph is in meters per second. Yep, and that's the slope of the gradient, the rate of change of position with time. If we look on the next page, velocity is not constant. So if the velocity of car is constant, the distance versus time graph will not be a straight line. It may be like that shown below. I don't really think one would, because that's suggesting that's carrying on accelerating forever and ever and ever, and it's going to end up going really, really fast in the end. Okay? So that's not as gradually moving less and less distance with time. Sorry. In the previous, we saw that the slope of distance time graph represented velocity. If we look at that line I've drawn on there, a line from A to B, passing through a single point on that function for x, if the line AB is a tangent the function, then the slope of the line AB is the velocity at point x. Yeah, because velocity is meters per second. What we're saying is, we find the slope of the distance versus time graph at any point, you've got the velocity at that point. Everybody follow that so far? So as we know, the slope of the curve can be found by differentiating the function f with respect to t. So find the first differential of a distance versus time graph. We end up with the velocity. The velocity is equal to dx by dt. X being distance moved. Okay? The first differential of distance versus time is velocity. Acceleration. Acceleration is defined as the rate of change of velocity. So if we plot the velocity of a vehicle against time, and we've got a curve, and we again put our line B on at a point V, any point on the graph, and that is a tangent to that graph, the slope of that line will give us the acceleration at that point. How fast the velocity is changing with every second. So if the expression velocity V in terms of time, then velocity can be by differentiating that expression. So we differentiate velocity for time acceleration. And to sum that up, acceleration is dv by dt. However, v is dx by dt. What I'm trying to say there is, if you start with distance versus time, you differentiate once to get the acceleration, or you find the first differential. You find the second differential, you've got acceleration. And the notation for a second differential of a single function is d2x by dx squared. dt squared, that should be the proper die. d2x by dt squared. So if we've got a function, x is equal to distance x is equal to a function, velocity is the first differential of that function, acceleration is the second differential of that function. Okay. And when we look at integral calculus, we'll look at the opposite of that, in particular, finding the area underneath a velocity versus time graph gives you the distance travelled. So you can go backwards and forwards with this. They are integral and differential calculus are opposites of each other. So you're going to find out next week. You may even remember from last year. Right? So that's the typical use of differential calculus as in speed, velocity and distance travelled graphs, functions involving that. So we'll have a look at one. Angular displacement, theta radians of a flywheel varies with time t seconds, and theta angle equal to 9t squared minus 2t cubed. Determine A, the angular velocity and the acceleration of the flywheel when t is equal to 1 second, and the time when the angular acceleration is equal to 0. So that's our function for the angle of this with respect to time. So we're not talking about distance moved along a straight line in meters. We're talking about the angle moved. Other than that, similar to what we've already been talking about. So the velocity is equal to what? How do we get from displacement to velocity? VT, yeah, well, equals, so we've got to differentiate 9t squared. $18t second. Initiated with a radians per second. Yeah, so t equal 1 second. Velocity is equal to 8. Everyone agree? Equal to. Over the 8. The first 18. 6t squared is 1 second. Acceleration. Six radians per second. Find here. Eighty. The side. Going on. Yeah. First, from display differential velocity, differential gives you acceleration. Fast. Bear in mind this to give kind of just a little overview about what you could use this maths for. In the diagram below, the curve has two turning points at P and Q, where the slope of the curve is 0, and hence the differential of the function dy by dx would be equal to 0. Point P is a turning point that is a maximum. And if we look at the slope prior to that, the gradient is positive. And if we look at the slope after, the gradient is negative. So we can find the time or the value of x when the slope is 0, similar to we now found the time when the acceleration was 0. So we can find this point here on its scale, and then we can look either side of x. If that was x is equal to 3, for instance, at that point, we could, when x is equal to 2.9 and when x is equal to 3.1, and see if the slope goes from positive to negative, we know we've got our local maximum. you look at this one, Q, the slope is positive after and negative before. So again, if we find this point, find us where x is equal to, I don't know, 6, we then look either side of 6 and find positive, negative, positive. We know we got a minimum. Okay, because that's what the change is. It goes from positive to maximum, and it goes from negative to positive minimum point. Okay. There's a further type of interest we have. It's a point of inflection. 2 points of inflection on this graph. We're going from a negative slope, a point where the slope is 0, point is negative. The slope is negative. Or on this one, there's a point where the slope is positive. Either of those two tell us, we look either side, get the slope, the sine sign, both sides, the point where we get a 0 slope, a point of inflection in the function. There's also a minimum point on that one as well. Okay? Now, like I've said, there's an option where if we're given prior procedure for finding and distinguishing between turning points. First find the x and y values at the point. So if we've got a function y is equal to f of x, we determine the function dy by dx. And then we let that differential equal to 0 and we solve it for the values of x. Maybe you may need to sketch the graph and try to find how many minimum and maximum there are in your point of interest, around your point of interest. Substitute the values of x in the original equation to corresponding y coordinate values. So you want the values of both y and x at that point. To determine the nature, minimum, maximum, or point of inflection, 2 options. You can either determine the sign of the gradient of the curve just before and just after the stationary points. You need to be careful. You need to perhaps understand the function a little bit, because if you go too far either side, you could miss another direction. So you know the function really. If you get the graph of it, something, you know how far to. 0.1 as a kind of, but if your current value of x is 0.1, you probably need 0.01 either side. Yeah. And then if you go from positive to negative, you've got a maximum. Negative to positive is a minimum. Positive to positive or negative. A second method be this ability differential. Go back to that question we skipped over. Consider at home and then the second differential function. Probably use that option, look at either side. If the first differential is reasonably simple, like the acceleration speed one, to find the second differential, And if the value is 0, point of inflection. Okay. Options. Hopefully we've got an example. Find the maximum and minimum value of the curve y is equal to x cubed minus 3x plus 5 by a in either the side of the point. We've got a function here, y is equal to x cubed x plus 5. I think it's the first thing. Looking back at the previous slide, find dy by dx. Potential of that function S3. Previous page, differentiator. Step 2 says, let dy by dx equal 0. Two. Let dy by dx is equal to nothing. How do we solve that? It's gone back to last year's maths without doubt. Quadratic formula. Can you remember it? Sorry? That's got no, I don't start with that. Minus b plus or minus square root b squared minus 4ac, and all that is over 2a. Yep. Quadratic formula. Another method, probably easier in this particular example. We're going to have to come back to it at some point. Anyone remember factorization? You can write that as a pair of brackets. We must have to put 3x in one of them and x in the other to end up with 3x squared. We've got to end up with no x on its own terms. They've got to cancel out. end up with a constant. We've got to have two numbers that go there and there that make minus 3 when multiplied together. What are the options? 1 and minus 3. And the other option? Minus 1 and plus 3. They're the only two options we got. Which one of those would leave us with what we are looking for? No x's and a constant of minus 3. If I put this 1 in there and minus 3 in there, what does it multiply out to? 3x times x is 3x squared. That's good. 3x times minus 3 minus 6x. 1 times it plus 1x. That don't equal no x's, does it? So that ain't no good. We could put the minus 3 in there and the 1 in there. What do we get? 3x squared plus 3x. Minus 3x. Well, that's looking promising. Minus 3. Those two cancel out. We're back where we started. If the two multiplied together are going to equal 0, one of them equals 0. Must the two here that will right. So if we equal minus 1, that in there will equal 0. Yeah. Right. What would I let x equal 0? If equal 0. X and minus. Two options in that particular case. This quadratic's got two roots. Yeah? 2 points where the function crosses the x-axis. So the answer to that bit is x equals 1 or x equals minus 1. We'll have turning points at both those x values. Next part says, in the original equation, y equals f of x, find the corresponding. So what we do is, when x is equal to 1, y is equal to, and the original function was x cubed plus minus 3x plus 5. 1 cubed is 1, minus 3 times 1 is minus 2, plus 5 is 3. So we have a turning point at, therefore, one comma 3 coordinates, where 1 and y is 3. Secondly, x is equal to minus 1. What is, need to be careful with your calculators here. Be careful how you square and cube and power 4 with negative numbers. Put it in a bracket and then cube bracket. If you don't put the brackets around it, it will do 1 cubed and then multiply it by minus 1. You get the wrong answer if the index is an even one. Minus 3 times minus 1 plus 5 equals. The answer to that is minus 1 cubed is 1. Minus 1 minus minus 1 plus 2. Is that, so the answer to that, if I'm correct, is 7. Am I right? So we got a turning point at minus 1 comma 7. Yeah? Options. We can find the look either side, so we can look at a 0.9 for instance, changes, find out if that's a minimum or a maximum. We can use find the second diff. We could do the same with this one, either side of that. So if x is minus 0.9 and minus 1. See whether the slope is positive or negative, how it changes. Second option is to find the second find the nature of, so 1x is equal to 1, find x is equal to evaluate second differential. So just going through this, dy by dx is 3x minus 3. So at 0.9, that's t times 0.9 minus 3 equals what? The answer to that is 2 minus 0.57. And then at 1.1, it is 3 times 1.1 squared minus 3 equals 1.63, 0.63. The size of it is irrelevant to us. The sign is what we're looking for. We're going from negative to positive. Around x is equal to 1. Therefore, x equal 1 is a what? Negative slope to positive slope minimum. Yeah? Find the second differential. 3x. Second differential is, that's 3x squared. As Catherine find it. So the second differential of that is x. When equal to minus 1 d2y dx squared equals 6 times minus 1 minus 6. Therefore, when x is equal to minus 1, there is a maximum for negative, isn't it? Negative second differential. Yep. Looking back at the options, if the second differential at a point is negative, then at that point is a local maximum. Alright? So in the case of this fairly simple function, start with a cubic, differentiate to a quadratic. Second differential, not too difficult, to a linear function. Probably that option 2 is quicker, less work. Okay? If you've got a function with sines and cosines in it, and that's a function of a function or a quotient and so on, finding the second differential of the result of the first differential might be difficult. Then you'd want to choose option and look either side. If we quickly, to finish off, have a look at that function graphed. There it is. Type the function in there. And we're going to be using autograph, but this online tool, there's also a iOS app and an Android app for phones, tablets, etc. It's quite a useful tool because I can these turning points and see that they are at x is equal to 1, and that's x is equal to minus 1, and that's a maximum, and x is equal to 1, y is equal to 3, we've got a minimum.